Jorge Vasquez, thank you for being our E-Club guest today. This is very exciting. We are here in your office at the Jet Propulsion Laboratory, and tell us what you do here at JPL. It's not about titles, it's about what do you do?
Thank you, Mel, for giving me the opportunity to do this. And at JPL, I actually wear two hats, forgetting about the titles. One of them is I'm the project scientist for sea surface temperature and salinity for the Physical Oceanography Data Center. The Physical Oceanography Data Center is responsible literally for distributing and maintaining all of NASA's oceanographic satellite data. The other hat that I wear is I also do my own research, and my field of expertise is in measuring the temperature of the ocean, measuring sea surface temperature. So both of those things come together in terms of sea surface temperature and salinity. They're both extremely important for understanding climate and global warming and changes in climate. So those are the two different hats that I wear at the lab. So I do my own research, and I'm also responsible for issues dealing with the project.
How does the level of salinity affect climate overall?
Well, it's basically, there are several things that affect salinity in the ocean. One of them is rivers like the Amazon, for example, where they outflow into the Atlantic Ocean. The Amazon puts in a tremendous amount of fresh water into the Atlantic Ocean, so that affects the salinity. The other thing is evaporation and precipitation. For example, if water evaporates over the ocean, then the salinity is going to increase because you're extracting water from the ocean. You're taking away water from the ocean, so salinity increases. And first of all, let me just define what salinity is. Salinity is the number of grams of salt per 1,000 grams of seawater. So if you take water away, the salinity is actually going to increase. Precipitation has effect on the salinity. If it rains more, you're adding water, so salinity decreases. So there's this relationship between evaporation and precipitation that is critical. So that the difference between those two has a tremendous effect on the ocean salinity. The third factor that changes salinity is the melting of sea ice, and this is where you really get into the issues of global warming and climate. Same thing with the precipitation. When ice melts, you're adding water to the ocean. So if ice melts, you're decreasing the amount of salinity. But another reason that is important is that in the North Atlantic is one of the areas where water goes from the surface to great depths, so water sinks. One reason is because of ice. When ice freezes, salt doesn't freeze. Salt stays behind. So salinity increases. So you have this whole circulation in the world's ocean that's driven a lot by this sinking in the North Atlantic. So if we do something, for example, if the climate is changing and global warming is taking place and things warm up, then you're going to have melting of ice in the North Atlantic. If the ice melts, then you're going to have you're adding more fresh water, so salinity decreases. So all of this sinking can actually stop. And actually, that's a huge area of research right now. In fact, if the ice melts due to global warming, and we have evidence to indicate that that's happening, the Greenland ice sheet is melting at an accelerating rate using NASA satellites. So with that kind of evidence, people are now looking at climate models to see what's going to happen to the circulation of the ocean. And why do we even care? There was a famous comment years ago by political strategists that said it's the economy. Well, with respect to global warming, it's the oceans. And the reason is that the oceans actually can take up 1,000 times more heat than the atmosphere. So the oceans are the key. If we understand how the heat is being absorbed by the ocean and how it's being moved by the oceans, we will know, in a sense, where climate is going to go in the future. And it's very lucky for us, because the oceans actually set the time scale for climate. So we're very fortunate that we live on an ocean planet and not really an Earth planet, because most of the surface, 75% of the surface of our planet is covered by oceans.
and the ocean absorbs the heat that's coming in from the sun, and so you're saying that dry land would reflect more of it back out.
Exactly. You know, the oceans literally. Another way to think about this for those that, electrical analogy, the oceans are the Earth's capacitor. They actually act as a heat capacitor. They store heat. Just like a capacitor stores electrical energy, the oceans store heat energy. They are the key. But they also release a certain amount of heat. And that's done by the ocean currents move heat from one way to the other. So two issues. If the ocean circulation changes because of global warming, then how the ocean transfers heat from one place to the other will change. And the other big issue is, again, the oceans, because they act as the Earth's thermostat, in a sense, a heat capacitor, then if the oceans, the fact that the oceans can take up 1,000 times more heat in the atmosphere, that's huge. So what that's telling you is that the oceans set the climate timescale. In fact, if it wasn't for the oceans, things would be changing much more rapidly. We would be warming up much quicker. Because of the oceans, things happen in a much slower timescale, thousands of years instead of 1 or 2 years. And so the bottom line is that the oceans are giving us a lot more time to understand this issue and get our act together. But that amount of time is not infinite.
So the ocean's ability to more or less the ocean's ability to help control the environment in the way the ocean's natural course of business does that, it impacts directly on what's happening with the climate. So how well the capacitor, this is the first time I know what the flux capacitor in Doc Brown's car means after all this time. The ocean, what it can do or what it cannot do as well as it used to, perhaps, is one of the reasons why the changes are faster.
Exactly.
Still at a slower pace than if there were no ocean, but faster.
Exactly. And let me give you an example. This is just an example where the research is going today. We know we can measure very accurately how much heat is coming from the sun. We have satellites, instrumentation on satellites. They can tell us very, very accurately at the top of the atmosphere how much heat is coming from the sun. If you had a perfect balance and we knew all the physics, you should be able to know exactly where that heat is going. What comes in from the sun should be balanced by what goes out and what's absorbed by the oceans, by the land, by the atmosphere. Problem, that equation is not balanced. We know the amount of heat coming in, but we can't figure out where it's all going. So one of the huge areas of research right now where they think is that a lot of this heat is going to the bottom of the ocean, not staying at the surface, but to the bottom of the ocean. And there's a lot of evidence, people are doing a lot of research and work right now to, in fact, solve this problem. Where is the extra heat going? We know it's going somewhere, and we think the oceans are doing a great job of taking it up. But again, people need to realize that the oceans are saving us, in my opinion, for the time being, but what they're doing is giving us more time to solve this problem.
Now, from there, the ocean is what's absorbing heat below us, below the so-called surface.
Yes.
And I'm flashing to a place where there isn't a Rotary Club yet, just from my very vague knowledge, which is the planet Venus.
Yeah.
One of the reasons that Venus is uninhabitable is because the cloud cover, whatever it's made of there, doesn't let any heat escape, which is why that continues.
Exactly, Mel.
What's the analogy to that here?
Well, for example, I mean, and this is where one has to get beyond the rhetoric of global warming and climate. There are things we do know. Carbon dioxide is a greenhouse gas. That's physics 101. There's no disputing that.
Greenhouse gas meaning that it traps the reflected heat underneath it once the heat gets through.
The perfect analogy of that is if you roll up the windows in your car, it gets hot very, very quickly because the windows, the glass, literally act like carbon dioxide, trapping the heat. It lets it in, but it doesn't let it out. Carbon dioxide does exactly the same thing. It lets heat into the earth, but it doesn't let it go back into the outer space. It traps it. Venus, as you mentioned, is a great example of that. Venus, in a sense, is a planet where the greenhouse effect has gone wild. It's gone to extreme. It's so thick with carbon dioxide that, in fact, the only way to see the surface of Venus is you have to use radar technology that actually can penetrate through the clouds. You cannot see through it any other way because it's so thick with carbon dioxide. What that means is that the surface of Venus is 1,000 degrees. There's no way, in terms of life as we know it, that it could exist on that. So Venus is a perfect planet to look at and ask, what are the effects of CO2? So, and you have to understand, that is a fact, that is a given. Carbon dioxide is a greenhouse gas, and carbon dioxide has been increasing in the atmosphere since the Industrial Revolution, since the late 1800s. Those two things are inarguable. You know, you just can't argue with that. The question again becomes, what are the consequences? What's happening? And again, this is where the oceans play a huge role that we need to understand better, because not only heat, the oceans also absorb carbon dioxide. Example, the ocean have these little animals called plankton. The little, both animal life and plant life. Well, a lot of these, make their living right off, almost at the surface of the ocean. Well, plankton, the plant life, basically, uses photosynthesis, and as we all remember from photosynthesis, takes in carbon dioxide and produces oxygen. So the ocean itself is a great mechanism for taking in carbon dioxide, not only through plant life, but also it absorbs the gas directly at the surface. The point is that the oceans take in heat, and they also take in carbon dioxide. How the oceans do that is a fundamental question for us understanding the issue of climate and where we're going in the future. But again, people need to understand the fundamental things we absolutely know and are facts. CO2 is a greenhouse gas, and there's been a lot more CO2 put into our atmosphere since the Industrial Revolution. The consequences of that is where we're looking at in terms of all of the resources going on with respect to global warming and climate.
And the ocean has the ability, in some sense, to scrub some of the carbon dioxide out of the atmosphere.
Exactly.
And put oxygen back in. It's reminding me of the device they had to fix on Apollo 13 when they were having too much CO2 on board.
Exactly, that's a perfect analogy.
And I definitely watch too much TV and movies, but I might have learned something. So now you have specific connections to some of the bigger research being done with the salinity and what's happening to the ocean. The launch, I believe it was earlier this calendar year,
yes,
of the Aquarius mission. Tell us about the Aquarius mission and your role in that and what it has started developing for us.
Aquarius will be the first NASA mission, actually the first U.S. mission, that can actually measure the salinity of the ocean. It's actually a mission in cooperation between the NASA and the Argentinian Space Agency, CONE. So it's an international collaboration. The Europeans have already launched their own version of this a couple years ago that can also measure salinity. Again, this is really exciting because salinity is one of the last parameters we haven't been able to measure from a satellite. We've been able to measure winds, and we can give that information to places like the National Hurricane Center to better predict hurricanes. We can measure the color of the ocean, which has to do, again, with how productive the ocean is, with plankton and things like that. And we can measure temperature. So all of these things we can measure, but this is the first time we can actually measure salinity. And again, why do we even care? Because changes in salinity will be a major indicator of where water goes in this planet. And that's one of the consequences of global warming. All of the models indicate that on a warming planet, the hydrological cycle will increase. It will get faster. And salinity will be a very good indicator of how fast that hydrological cycle is actually changing. And it's just, the hydrological cycle is just a fancy way of saying, where does water go on this planet? How does it move from one place to the other?
Is there an easy answer that we have to this yet? If the salinity, the percentage of salt in the water in the ocean, if that percentage is greater as opposed to if that percentage is lower?
Well, let me give you an example. Let's go back to the issue of evaporation and precipitation. Let's say our planet, and there's all indications, let's say it's warming up. Under those conditions, what would happen? You would have more evaporation.
and water evaporates, the salt stays where it is.
Exactly, the salt
Okay.
stays where it is.
Okay.
So under those conditions, salinity, we should say increase, an overall increase in the salinity content of the world's oceans. Why? Because evaporation is increasing. If evaporation is increasing, you're going to get more cloud formation. With more cloud formation, you're going to get more storm activity. So this is what they mean by you will speed up the hydrological cycle. So these are the kind of questions that are very applicable to human society and understanding the consequences of climate change. And a perfect example, as I've said in the past, is for those that don't think water is important. My gosh, look at California. If you've ever driven up Interstate 5 in the middle of California, one of the world's largest agricultural areas is all irrigated. There's no natural water. So think about how important water is to California. Any changes in the hydrological cycle will have huge consequences in terms of agriculture in our own state. Second issue is not just agriculture in our own state, recreation. I love to ski. So any changes in the hydrological cycle is going to have a huge impact on the ski industry in this state, on boating, on fisheries. So all of those things, understanding how water moves on this planet is a major issue for understanding the consequences of global warming and climate.
As a hockey player, I worry about all the loss of ice from
Exactly,
We'll work on that. Now, there's something that I don't understand that because I get most of my science information from the people on cable news stations who also don't really fully understand it until they bring their science experts in. It feels to me, just observing, that the extremes over the last few years are greater. The summers are hotter. Despite the use of the phrase global warming, which I think that too many political things seize on, the winters are colder and more biting. It's the extremes. The hurricanes, for example, which I believe are heavily affected by the ocean and what the ocean does to the storm formation. How does all of that come together? What do these extremes indicate?
That's a very good point, Mel. And one of the things, people always look at climate models and say, well, they don't agree on anything. Not true. For example, climate models all of them agree on one thing, that extreme events will increase. Under a warming planet, you're going to have more extreme events than you would under our current scenario. So that's something that is absolutely clear in all of these climate models. And yes, the one thing you can't say is you can't specifically say this event was caused by global warming. So you can't, for example, this year, you can't say Hurricane Irene was caused by global warming. But if you get a trend in more severe hurricanes over a longer period of time, then you have to start worrying. If you get a trend and going from one extreme to the other, then yes, you can start looking at that and saying, is that related to a changing climate? And there's no question over the last few years, and again, that's an area of a lot of research, people are looking at these issues. And certainly last summer here in the United States, we went from one extreme to the other. You look at the heat waves in the East Coast. You look at the flooding of the Mississippi. So these things are happening, and is it an alarm? Is it something that we should be concerned about? Well, again, you can't say one specific event was caused by global warming, but it's something that people have to understand. This is predicted. These kind of scenarios are predicted by climate models.
So the question becomes, when the data starts pouring in from the Aquarius mission and the satellite, what will you then be able to do with that?
Well, one of my areas of interest is looking at areas like using that information to look at, obviously, is the salinity in the North Atlantic changing? All indications are from other satellites that the Greenland ice sheet is melting, and it's melting at an accelerating rate.
And that's all fresh water.
That's
so
all
that
fresh water.
Decreases the salinity.
Exactly.
More water added to the same amount of salt.
Exactly. So people will be looking at that very specifically, the salinity, especially at the high latitudes in the North Atlantic, and also in Antarctica, where you have Antarctic ice sheets melting. One of the areas I'm interested for me is in looking at salinity contents like in the Mediterranean Sea. The Mediterranean is a fascinating area that where you have fresh water coming in at the top, but there's a lot of evaporation as that water goes from the western Mediterranean to the eastern Mediterranean. So you have a very strong signal as the water changes in salinity content as it goes from the west to the east of the Mediterranean. And because it gets heavier, as salinity increases, it gets heavier, the water actually sinks in the eastern Mediterranean. So the Mediterranean has a circulation where you have fresh water coming in on the top through the Strait of Gibraltar and more saline water going out the bottom of the Straits of Gibraltar. So I'm very interested in looking in that area when the data starts flowing. Part of it is because I have connections with scientists in Spain. I was there doing a postdoc in Barcelona for 6 months, so I still am very interested in that area of the world.
And exploring it from the Riviera wouldn't be a
Yes,
bad
exactly.
thing.
I wasn't going to say that, but along the Costa del Sol or
We
Costa
can
Brava,
edit
what-
that.
yeah, you can
We
say-
can edit that out of the tape later. We won't, but we can edit it out of the tape later. I would love to keep talking about this for a long time, but E-Club or otherwise, we have the time constraints of our program. I hope we can have a similar conversation about this as things develop, because the one thing we can tell about climate is that however it changes, it's going to change. It'll be different
Absolutely.
tomorrow.
Absolutely.
So I hope we have a chance to talk again.
Well, thank you, Mel, for inviting me, and again, thank you for the opportunity.
Thank you, Jorge Vasquez, and we'll talk again soon.
Okay, thanks.